Momentum. First thing we're going to do is we're going to assign a couple of different definitions. So first of all, we could define momentum as a strength of motion. A strength of motion. Alternatively, we could simply define it as a property equal to an object's mass and velocity, or a property equal to an object, the product of an object's mass and velocity. A property equal to the product of an object's mass and velocity. All right, how many of you guys took physical science? Okay, so in physical science, you learned momentum, and you were able to calculate momentum as P. Yeah, we use the letter P for momentum. Don't ask. Equals mv. Capital P is power. Lowercase p is momentum. Lovely. Italicize? Yeah, lowercase p is momentum. It's just what was evidently written by the physics gods. I don't know. Say again? M is mass. Oh, capital M is molarity. Yep. So we use random letters sometimes. So P equals mv, where momentum is P and has units of kilogram meters per second. Okay. There are no special units for momentum, and because of that, one of the nice things is when we say that the units for momentum are kilogram meters per second, that's specifically just the SI units. It does not actually matter what velocity and what type of mass you use when working a momentum problem, as long as everything in your problem is consistent. So as long as all of the velocities agree and all of the masses agree, you're going to wind up working through a problem just fine. Now in 9th grade, you guys calculated P equals mv, and that was really as far as you got. And that's not very useful. Saying what an object's momentum is doesn't actually tell us anything about what that object is doing. Knowing strictly its mass and its velocity as separate values is actually more useful. The reason that we have momentum is that physicists basically created a unit that we found exists in collisions. Momentum is specifically designed for application in collisions. Momentum is designed for use in collisions. I say design and used in collisions because there is no innate property of the universe that says momentum has to always remain the same. That's energy. Momentum must remain the same in a collision. Different situation. Okay? So if we have the law of conservation of momentum, we find that just like mass, just like energy, momentum cannot be created or destroyed. It can just be transferred in a collision. Cannot be created or destroyed. It may be transferred in a collision. Meaning that mathematically, the sum of the momentums in one dimension equal the sum of the momentums in the same dimension finally. What's the big difference between this and energy? Okay, don't lose anything to some other source. Any other answers? So, yeah, go ahead, Amber.
Well, I was going to say, isn't energy a one-dimensional?
So it is about the dimension piece. Energy is a vectorless unit. Energy is scalar. And because energy is scalar, we don't have to worry about what direction it acts in. However, momentum is not a scalar unit. Momentum is a vector unit, meaning that each dimension is conserved individually. So if I say the sum of the momentums in the x direction is equal to the sum of the momentums in the x direction in the final situation, then at the same time, I also have the sum of the momentums in a y dimension equal to the sum of the momentums in the y dimension, finally, and z as well. We won't deal with the z dimension, don't worry. Okay? So momentum is a vector unit because it's just taking a scalar times a vector. We're not squaring the vector unit in any way. So because velocity is a vector unit, momentum is a vector unit. Momentum is a vector unit and conserved in independent dimensions. Okay. Questions at this point? Can everybody already see their vector addition coming back in and their trig functions and right triangles starting to materialize? Yeah, it's back. Yep, that too. All right, so when we're talking about momentum, we talk about momentum in two different types of collisions. We talk about momentum in elastic collisions and in inelastic collisions. Elastic, inelastic. So first thing we're going to do is we're going to look at some elastic collisions. And what I'd like you to do is just jot down some observations that you've got as we look at elastic collisions. We noticed that they kind of swapped velocities. The one that was moving stopped. The one that was at rest began moving with the original velocity. Okay? Let's see here. Anything else that we wanted to point out? Okay. All right. So third setup we're going to put up here. Now the heavier one will be stationary. And predictions. What do we think is going to happen? Okay. Okay. Next setup, inelastic. So as I was saying a minute ago, elastic, in some form, elastic collisions always have the objects bounce off of each other. Now, that's not a perfect situation because no two objects ever completely bounce off each other perfectly. There's always some kind of deformation or energy loss due to friction and thermal energy. However, these get pretty close. And we will talk about perfectly elastic collisions so that we understand the extremes and can then interpolate between the two extremes. Yeah? Magnets get really close. There will still be, is there still some energy loss when we're talking to magnets?
That's what I was saying, like, you make it sort of like, you make air on the bottom and then magnets on the side, you still like not have
will there be perfect transfer momentum? There might be perfect transfer momentum if there's no contact.
and there's no back.
Yeah, sure, we put it in, yeah. No, I think you could probably do it with magnets because then there's no contact. That
Is that
very
what
well
you're doing
work.
here or no?
Say again?
Is that what you're doing in those or no?
Nope. these are just using rubber bands. What I'm upgrading this to is we're now going to talk about inelastic collisions. So if an elastic collision is where the objects bounce off of each other, inelastic is where they stick together. So the setup that I've got, on one end, this has a needle. On the other end, I have a ball of clay. So that when these actually collide, they will stick together every time. So observations about equal mass. So we've got them, this one's stationary, this one's moving. Again. One more time. All right. And what should I record? Okay. So combined continue at about half velocity. Anything else that I should write down for that setup?